Hello everybody, my name is Marian Villa. I'm Senior Full Stack Product Designer at Nodesource. I also want to introduce my colleague Santiago Gimeno, Senior Software Architect at Nodesource. As you already probably know, we work in observability, focusing exclusively in the Node.js runtime. But today we're going to discuss only what's available in the open source space to implement observability in your applications. Today we're going to present line trains, instrument your Node.js applications with open source software. And before starting our presentation, it's important that we keep in mind a few of the main concepts of observability. It is important to understand that when we talk about observability, we need to understand what questions we seek to answer or clarify when detailing a system. The first questions we undoubtedly ask ourselves is why my application have a certain behavior, and to solve this, another question, the first thing we must do is instrument our system that our application can emit signals, that is traces, metrics, and logs. When we do this in this correct way, we have the necessary information that we needed. But what is observability? So in synthesis, observability is the ability to measure the internal states of a system by examining its outputs. Your system and apps needs proper tooling to collect the appropriate telemetry data to achieve observability. But what is the telemetry data that we need? The three main pillars of observability will be: first, metrics as dots, logs as lines, and traces as traces. When we name our keynote in this way, because with dots, lines, and traces, you have the whole picture of your system, and we want to create a direct reference to the basic core concepts of visual representation in a plain planimetry. But let's jump to dig a little bit more of this concept, not just enunciated them. First, start with metrics. Metrics are aggregations over a period of time of numeric data about your infrastructure or applications. Examples include system error rate, CPU utilization, and request rate for a given service. Briefly, a metric is a measurement about a service captured at runtime. Then jump to our second core concept, logs. A log is a timestamp message emitted by services or other components. They are not necessarily associated with any particular user request or transaction, but when they are, they become more useful. We'll get into this in a little bit later. Before defining what a trace our third concept is, we should define the concept of a span. A span represents a unit of work or operation. It tracks a specific operation that a request makes, painting a picture of what happened during this time in which that operation was executed. A span is the building block of a trace and is a named time operation representing a piece of the workflow in the distributed system. All traces are composed of spans. That's why the importance of this concept. And before jumping directly into traces, let's talk about context propagation. It's an important functionality that is required to implement distributed tracing. We can define it as a mechanism of storing state and accessing data across the lifespan of a distributed transaction, either across executing context inside a process or across the boundaries of the service that conform our system. For in-process propagation, we will typically use something like async local storage class from the async hooks model. And for across processes, it would depend on the IPC protocol used. As an example, for HTTP, there's the trace context specification from the W3C, which defines the transparent and transstate headers to propagate tracing info. Now it's time for the third core concept, traces. A trace records the paths taken by requests made by an application or end user. As they propagate through multi-service architectures like microservices and serverless applications, it is also known as distributed trace. Without tracing, it's challenging to pinpoint the cause of performance problems in a distributed system. We just define the concept of tracing, then this all sounds like very abstract. What does this really mean? What is this good for? Let's see it with a very simple example. With the same architecture we will use in our demo, we can clarify this for you. So let's say that we have a distributed application like the one in the picture. which I said with the application will be demonstrated later. It has 4 Node.js services, API, auth, service 1 and service 2, and 1 database. Imagine we having intermittent performance issues. They could come from several points, wherever is the database access, network link status, or DNS request latency, etc. Finding where exactly may become a very hard and time-consuming task. The harder, the more complex the system is. Distributed tracing is going to help us a lot with that, as we'll be generating tracing info on every point of the distributed system, A, B, C, D, and E. Not only that, with the request goes through all the services, thanks to context propagation, some tracing state is going to pass along so all the tracing info can be linked in a very same request. Also, that info will be exported to a backend service where we can easily visualize and analyze the data, allowing us to identify where the issues may come from. More on this later on the demo, and before that, it's really important to talk about instrumentation. First, instrumentation is the process of adding observability code to your application. We can do it either automatically or manually. With automatic instrumentation, our instrumentation libraries will take the configuration provided through code or environment variables and do most of the work automatically. In the following example, using the OpenTelemetry SDK, we show how we can automatically generate spans of every HTTP transaction handled by the Node.js HTTP core module. Manual instrumentation will require more work on the user-developer side. Enables far more options for customization, from naming various components with OpenTelemetry, for example, spans and the traces, and to add in your own attributes, specific exceptions, handling, and more. See the following example where it shows how to manually generate the span also using the OpenTelemetry SDK. Okay, all about OpenTelemetry sounds good, but how do we correlate data? The way we historically will implement a typical observability pipeline is shown in the following picture. In this case, having all the data at your disposal is great and can give us a valuable overview of our system. But unless we are able to somehow correlate the observability signal, metrics, logs, and traces, we won't be able to have the best of it. OpenTelemetry comes to solve this problem. The solution is going to come from correlate these signals. This can be done by applying the same concept of context propagation that was used for traces to metrics and logs, so that identifiers such as the trace ID and the span ID are associated with those signals. So, for example, for logs, if we can correctly identify which specific request generates the actual log ratio, we will have more useful information to take decisions. But OpenTelemetry is much more. It defines an API, which defines data types and operations for generating and correlating tracing, metrics, and logging data. We have SDK. It provides language-specific implementation of the API. We have OTLP, a protocol to transport the telemetry data. We have a collector to receive, process, and export telemetry data. And finally, we have semantic conventions to have a well-defined naming for the attributes associated to the signals, service name, HTTP port, etc. Next, Santiago will present a demo in which we'll showcase some of these OpenTelemetry features along with other open source tools. Santi, the stage is yours. Santi, the stage is yours.
Hello. Well, thank you, Marian. We're missing you here quite a lot, but let's focus now on the demo I'm going to show you. We can see here the application that Marian was showing before with all these 4 services and the Postgres database in which we have observability. What we are going to do is we're going to collect the data, extract the data from the 4 services by using the OpenTelemetry API. And later on, that will be exported to the specific backends. We're going to use, in this case, Jagger for traces and Prometheus for metrics. Also, notice here that the way in which the data is going to be exported is going to be a bit different. So for traces, we are going to use OTLP over HTTP and send that data to Jagger, whereas Prometheus is going to pull the metrics data from our services by using HTTP. So let's go now directly to the code. Can you see it well? Yeah. So first thing, I'm going to show you how easy it is to add observability to your application by using the OpenTelemetry SDK. So I have grabbed everything in this setup function here, but before looking into that, I'm going to highlight some of the most important classes that the SDK provides. First of all, we have the node tracer and meter providers. Those two allow us to actually extract the data from our services, whether they are traces or metrics. Then we have the OTLP trace and the Prometheus exporter. Yeah, they're going to export data in those protocols. And finally, we have the resource class. So in resource instances, what we're going to do is store specific attributes that allow us to describe perfectly the process we are running on. So later on, we can link from which process the data point came from, right? In our case, we are going to use only two attributes. Just for the demo, we're going to use the service name and container ID. Notice that these two attributes and others are well defined by the specification, and we can get access to them by using the semantic conventions module, right? So going quickly through the code, first of all, what we do is create set up tracing. We create the node tracer provider with a resource attached. We set up the OTLP over HTTP exporter and point it to the Jagger endpoint, so it can consume that. Also here, we use this helper to raise the instrumentations to enable automatic trace generation from some of the most popular Node.js core modules, whether it's Imagine HTTP or some other popular modules as Fastify or whatever. In case we want to generate spans manually, we can do it as well. For that, we create an instance and we'll work with that. Yeah, that's for traces. For metrics, basically the same. We create a metric provider with a resource attached. We set out the Prometheus exporter, and finally, we create a meter instance that is going to allow us to create meter instruments such as counter, gauges, histograms, etc. And just last thing before going to the demo is what we do in our actual service. So this is one of the four services. Basically, all of them are the same, are Fastify servers. Nothing too fancy there, but what is important to notice is that we need to set up observability before actual code. And there's a reason for that, is that these instrumentation modules that we're talking about, the HTTP and Fastify in this case, what they actually do is they monkey patch the module they are actually instrumenting. So we need to do that beforehand. Then we're going to also set up three meter instruments for every service, the same for every one of those. An HTTP request counter to track the number of requests processed, and a couple of gauges to track CPU and ELU usage. So that's it for the code side. Let's just spin up the demo. Sorry. Okay. Yeah, there we go. And send the first request. So yeah. We can see is that the request actually went through, but yeah, it was answered without 401 unauthorized, so there are some issues there. What we're going to do now is try to look at the telemetry data we have collected, and yeah, let's try to figure out what's going on, okay? So, okay. First of all, I'm going to show you the Prometheus UI. Here, let's see if we are actually receiving the metrics info. Yeah, so we have here the HTTP request counter. And what we can see here is that there's been one request processed by the API service and another one by the app service, which makes sense. Also notice that the attributes we set in the resource are already there. We have the container ID and the service name. So we can relate those. Let's take a look at the other two, just in case. It was process CPU. Okay, yeah. 4 services are sending data about this. In this case, because it's a gauge, probably it's more useful having this graph. On which line we can see how the CPU usage evolves on every one of the services. So looking good. The same for the thread event loop utilization. Yeah, everything's there. So as far as metric goes, it seems to be working fine. Let's go to the Jagger backend to see if we have received any traces. And yeah, we have received one that corresponds with the HTTP request that we just sent to the application. Looks good. It consists of 3 spans with an error, goes through 2 of the services, API out, that matches with the information we got from the metrics. Before inspecting this a little bit more, I like to make you notice this graph above, in which every point will represent a trace, where the x-axis would be the time the trace was created, and the y-axis would be the duration of the trace. Later on, more on that. Okay, so let's just inspect this for a moment. As we saw before, there are 3. It consists of 3 spans here. Every one represents an HTTP transaction, and all of those have been automatically generated by the instrumentation HTTP module. So there was no code that needed to be added in order to make this work. Just for, yeah, so you can see what the instrumentation module does. It doesn't only track the transaction, but it only collects data that is going to be very useful in order to almost completely identify what the transaction looked like. So for example, you have the method here, I don't know, the URL, the status code, the status test, content length, etc. And finally, I'd like to point you out to these logs. So as Marian mentioned before, having a log that is linked to a specific span is where the log becomes more useful, because we actually know which exact request caused the creation of this log. So if we look into this log, we can see that basically describes it's a JavaScript error, right, with a message and a stack trace. And yeah, by looking into the message, we know that we were missing the token to be authorized in the system, so we know what to do next. But before that, I'd like to point out that attaching logs to traces is not done automatically by instrumentation module, but we had to add some code, not too complicated, quite simple with the OpenTelemetry API. So what we do is that in case of the verification of the token was failing, what we do is like extract the active span from the current context. This brings us back to the context propagation stuff. So we extract that, and then we associate the error to the span by using the record exception method. And yeah, basically that's it. Well, so let's now try to send a request that actually authenticates or is authorized by the system. There we go. Yeah, it went through. It sent us back some data. So let's take a look at Jagger to see what was different between those. So if we go here, we can see that already there are some differences. Of course, no errors, 7 spans. It went through 3 of the different services. But there's some very nice tool that Jagger provides that allows us to compare traces, which I think is amazing. So what you can do here is, you can see here is that in gray, the nodes in gray are the nodes that are the same between those traces, whereas in green, the ones that are new. So we can see that in this last request that went through, once it was authorized, the API service sent a GET to the service 1, which then perform a couple of operations to the Postgres database. Yeah, it connects to the pool and perform a query. Before jumping on, I'd like to show you what one of these spans related to Postgres look like, because I think it's quite nice. So this one that represents the query operation, as we can see here, was automatically generated by the instrumentation PG module. And yeah, everything that some stuff that is very useful, like the whole query, the connection string, the type of database, also very useful. So you get all that info like automatically. Okay, so now just one final thing. I'd like to show you something that I think can be more interesting. What I'm going to, let me see. Yeah, there we go. So what I'm going to do now is like inject quite a bit of load into the application. 25 seconds with AutoCannon, 15 connections. Let's see how the application behaves, and then makes an investigation or whatever. So. Okay, there we go. So here's the latency table, and some interesting things that appear here. It's like, if we look at the 90th percentile, we can see like, okay, most of the requests are being responded fast. I mean, around 200 milliseconds or less, yeah. But, there are a few of those that are terrible. They're more than 3 seconds and something's going on. So let's see if by looking at the data we have collected, we can figure out what's going on and why this happened. So first of all, I'm going to go to Jagger, filter like a little bit more of traces, and there we go. So now we're going back to the picture I was explaining before. What we can see here is like quite consistent with what we were seeing in the latency table. I mean, most of the requests are really served fast, but there are some outliers here that are awful, terrible, right? So let's see if we can compare two of those, one of the fast ones with one of the slower ones, and start from there. So I pick one, the slow, 35, and this one. So we're going to compare those, and what we see is that everything is practically the same, but in the slower one, service 1, after performing the query to the database, it sends a request to service 2. So it seems that the main culprit here, the main suspect would be this branch. So something there when service 1 sends a request to service 2. So let's see if we can confirm that somehow. So one thing that we can do as well is, if we inspect to this trace and use this trace graph view, we have this graph in which every node represents also a span. But the good thing about this is that in the left-hand side, what we can see is the time that the trace that would have this node as root takes, and it compares that against the whole trace. So if we're in the root node, of course, 100%, but if we go down through the different branches and pick the one that takes more time, we can just, 99.2%, 99.9%. Well, what we can see here is that basically, our suspect was the one. An important thing to notice here is that it's not that service 1 is taking so much time in processing. I mean, it's taking time, but it's not that bad. Most of the time it's here. So it seems to me that requests that go from service 1 to service 2 somehow are buffered and takes a long time for them to be processed. But let's investigate a little more. So now we go to Prometheus. We're going to check the event loop utilization of the main thread. And what we can see is this peak here for a while. But it's not that bad. Something's wrong. Anyway, the thread loop has gone up. It should have been 100%, but I think there are some issues. But the thing that is giving us this peak is that, it's actually telling us that there's a lot of usage of the loop of the service to JavaScript thread, and it's making it to take a long time sending responses back and having this buffering of the responses that are going into. So let's try to get now to the code to see if we can figure out what's going on. So this is not very original, but what I'm doing here is a high CPU route, and I'm calculating Fibonacci numbers here. So it makes sense. These are high-intensive operations, and it makes sense that we were seeing what we were seeing, right? I mean, this is not what your actual production code will look like at all. Usually, it will be much more complex. Not so easy to spot where the problem is, but at least what you can see is that by using this technique, what you can do is narrow down. At least what we have been able to do is narrow down to a specific service, even to a specific route. In more complex cases, it would be great to use this along with other things like perf, running perf on the service, or CPU profiler, etc. So that's my demo. I hope you have enjoyed that. And yeah, I'm going to go back to the slides to wrap this up. So which are the main takeaways? Well, first of all, setting observability in Node.js by using the OpenTelemetry SDK is not that hard. Actually, the OpenTelemetry documentation is quite good and complete and have some very good examples there. Also, it allows us to observe requests as they propagate through a distributed system, and it allows us to identify points of failure or some bottlenecks in your system, yeah, right? And one last thing is like, yeah, adding observability to our code is great, but you have to be careful because, yeah, it's not free. So depending on the tool and on the, especially on the amount of data that you're trying to collect, you know, your performance is going to suffer from that. So there's always a balance there, okay? So that's it from me. I hope you have enjoyed this. Some links over there. The link below is where the demo is if you want to play around with it. I have to make it public yet, so I'll do it in a few minutes. So it should not be already available, but I'll do that in a few. And thank you, everyone. Thank you from Marian. She was devastated not to be able to be here, but anyway, that's life. Okay, so thank you very much. If you have any questions for me, I'll be around, and yeah, I hope you enjoyed this. Thanks.